Our next topic is homeomorphisms. Consider two topological spaces X and Y. Say X has the topology tau on it and sigma is the topology on Y. And then you consider a bijection f from X into Y, a bijective function. Such a bijection will be called a homeomorphism if both it and its inverse are continuous. The inverse of course exists because this is a bijective function. If the function as well as its inverse are continuous, then the original function will be called a homeomorphism. Now you note this thing about f inverse being continuous. When do we say that f inverse is continuous? We of course apply the definition of continuity to it. What is the range of f inverse? The range of f inverse is X and its domain is Y. So if you take an open set, any open set in X, that means if you take an open set U in the topology tau, then the inverse image of U under f inverse has to belong to the other topology, sigma. And this, however, is nothing but f of U. So f inverse is continuous if and only if for each open set U in X, its f image is open in Y. So we can say this, a homeomorphism f from X into Y is a bijection such that for any subset U of X, U belongs to the topology tau if and only if its f image is in the topology sigma. The forward implication here of course comes from this part, and that is equivalent to f inverse being continuous. If U is an open set in X, that is, if U comes from the topology tau, then f of U is open in Y. That means it belongs to the topology sigma on Y. And that is just what f inverse being continuous ultimately means. And the backwards implication tells us that f is continuous. What is that? When do we say that f is continuous? For f to be continuous, you take an open set in Y and see if its inverse image under f is open in X or not. You choose any open set in Y, say you give it a name, say V. Then V will be equal to f of something. What is that something? That something is nothing but f inverse of V. Okay. And from there, if you follow this backwards implication, you clearly get the fact that f is also continuous. So that's why instead of saying that f and f inverse are both continuous, you can also say this. Then it becomes a homeomorphism. A homeomorphism is the topological version of an isomorphism that we know from algebra. When we say that there is an isomorphism between, say, two groups, then we just mean that essentially they are the same group. There is no point considering them as distinct groups. Just like that, when we say that there is a homeomorphism between two topological spaces, then topologically they are indistinguishable. Or you can view it this way also. One space may look like something, the other might look like something else. You can continuously deform one of them and get the other. If you see the Wikipedia page on topology, there you have one animation. It shows that a coffee cup is slowly turning into a donut. So that f does this. There is an f which turns the topological space of a coffee cup into the topological space of a donut. So it's like that. There is no distinction topologically between two homeomorphic spaces. So we see that open sets in tau correspond to open sets in sigma. For each open set in tau, there exists an open set in sigma and vice versa, and that's why we can say this. So we also have a bijection between the topologies themselves. And because of this, we can say this. Thus, any property of the space X that is expressed entirely in terms of the topology tau has a corresponding property in the space Y, which is entirely expressed in terms of its topology sigma. And such a property is called a topological property, which continues to be true between homeomorphic spaces. Homeomorphic spaces are indistinguishable in the sense that no matter which one you choose and study it, it's equivalent to studying all homeomorphic copies. It's like what you have in algebra. Say there are two groups and you know that they are isomorphic. If any one of them is non-abelian, then the other one cannot be abelian. It also has to be non-abelian. Or say you have two isomorphic graphs. If one of them does not have a cycle, then the other one also cannot have a cycle. So in that sense, homeomorphisms are structure preserving maps between topological spaces. Again, let f be a function from x into y, where x and y are, as before, topological spaces with respective topologies tau and sigma. But this time, this function f is, say, injective, okay, and the image set is, say, we are calling it z. Now z, of course, being a subset of y, inherits the subspace topology that y will give z. That means z inherits its subspace topology from sigma. Now you consider the function f prime from x into z, which we obtain from this function by changing its range from y into z. We do nothing else, okay. We keep the rule for the function same. We just change y into z. Now if this f prime is a homeomorphism, then we call the original function f from x into y a topological embedding, or just an embedding of x in y. It is somewhat like, again, what you have in algebra. Say there are two groups g1 and g2, and there is an injective function, a one-to-one function from g1 into g2. Then if you replace g2 with the image of g1 under that function, then it becomes a bijective function. Now if that's an isomorphism, I mean if that function is an isomorphism, then the two groups g1 and its image become isomorphic. So in that sense, you have found a copy of g1 inside g2, an isomorphic copy of g1 inside g2, and you can say, I mean if you do not distinguish between those two copies, you can say that g1 is a subgroup of g2. In that sense, here topological embedding means you have found a homeomorphic copy of x inside the space y. So you can say, in that sense, if you do not distinguish between x and its image under f prime or f the same thing, then you have found x as a subspace of y. Let's see some examples next. Example 4 next. Let's consider these two functions f and g, both having the set of real numbers as their domain as well as range. F of x is 3x plus 1, and g of y, if you want you can write g of x also. G of y is 1/3 of y minus 1. Now one can of course show that g is nothing but f inverse. It's a simple calculation. You calculate the two compositions, f composition g and g composition f, you will see that both of them are identity function from R into R. So g is nothing but f inverse. Now because f and g are both continuous, so what are we getting? That f and its inverse are both continuous. That is why f is a homeomorphism. And regarding the continuity of these functions, it's a simple thing from calculus, right? These are, both of them are linear functions, linear polynomials, so that's why automatically they are continuous. Next, in example 5 also we have two functions. This time, however, one of the spaces is this open interval -1, 1. With the subspace topology, it inherits from the standard topology on R because it's a subset of R, and R of course has its standard topology, that's the other space. So f maps this open interval into R, and the other function g maps R into this open interval, and the rules are these. F of x is x divided by 1 minus x square, and g of y is 2y divided by 1 plus square root of 1 plus 4y square. You can see one thing, that whenever you see a function, you at least see that the formula does not cause any problem. What type of possible problem can you have from this ratio? Only one problem, namely if the denominator is 0, then you have a problem. But that is possible only when x is either 1 or -1, because then its square would be 1. neither 1 nor minus 1 is present in the domain of f, so there is no problem. And in this case also one can prove that G is nothing but f inverse. So this shows two things simultaneously. One of them is that f is invertible, and the second thing is that its inverse is nothing but G. Now again in this example also, because both f and g are continuous, so f and f inverse are continuous, and that's why capital F is a homeomorphism. How will you verify that they are continuous? For that you look in analysis, real analysis. There you have something called algebra of continuous functions, where you add, subtract, multiply, divide continuous functions to produce more continuous functions. That can be used to verify that f and g are continuous. Here of course you have square root, but that also follows from the fact that square root is a continuous function when the input is a non-negative real number. And you also use the fact that compositions of continuous functions are continuous. So that's how you can get that f and g are both continuous. What does this say? This entire thing, what does it say? It says that the two topological spaces, one of them is the entire real line and the other one is the segment between -1 and 1. They are topologically the same space. Next we have example 6, which actually is a non-example. It states that a bijective function can be continuous without being a homeomorphism. And the perfect example is what we have already seen in the previous video. Previous video or the one before that, I don't remember, but we have already seen this example. You consider the identity function g from RL into R. So g actually does not do anything. You take a real number x, g of x is x itself. But as we have already seen, this is continuous. However, its inverse, which is also the identity function, which however maps R into RL, is not continuous. And moreover, this of course is bijective. So in spite of being bijective and continuous, because the inverse is not continuous, this is not a homeomorphism. This does not automatically of course tell us that RL and R are not homeomorphic. It just tells us that this is not a homeomorphism. Within example 6, there is another example, and for that we consider the unit circle. Unit circle in the plane centered at the origin, having radius 1. That's why it's called unit circle, and we give it a name also, S1. Now next what we do, we define a function f from the closed open interval 0, 1 into S1 via this formula. F of t is cosine of 2 pi t, sine of 2 pi t. You can immediately see that this is a point in S1 because this square plus this square equals 1. Okay, so it's on the unit circle. And from properties of trigonometric functions, actually we know much more about the function capital F, namely that f is continuous as well as bijective. So that means this function f is a bijection, and as a function from this topological space onto this one, it is continuous. Oh, and what are the topologies? This one of course inherits a subspace topology from R, and this one also inherits a subspace topology from the plane R2. So we have accordingly written here this line. It follows from analysis that f is bijective and continuous. But at the same time, f inverse is not continuous. And the reason for this being not continuous is this. You consider this, which is an open set here. And what is this? What's the relationship between this space and f inverse? It's the range of f inverse. The domain of f is the range of f inverse. But the f image of this, which will be a subset of S1, is not open in S1. There is a figure in the text showing why it's not open. Let me draw it roughly. So this is the space S1, the unit circle centered at the origin. And the image of f image of this interval is this arc which lies in the first quadrant, such that this endpoint, which is your 0, 1, is not there. It's not a part of this image, but this endpoint is there. Actually, what's going on? If you take your input, of course, your input has to come from there, but now you are confining your input within this interval. So, as you take your t equal to 0 and put the value here, what do you get? Cos 0 is 1, sin 0 is 0. So, that means capital, oh, I forgot to write capital F, I wrote small f here, okay, it will be capital F. Let me just rectify it. So, capital F of 0 is 1, 0, okay, and then as your t increases through these values, and eventually it does not of course reach 1 over 4, but just for the sake of argument, if you take t equal to 1 over 4 and put it here, what exactly will you get? Cos pi divided by 2, because you are dividing by 4, which is 0, and sin pi divided by 2 is 1, so you get 0, 1. You don't get that point actually, but you go until you reach that point. Okay, so this is your f of this. Why is it not open in S1? You think of the subspace topology that S1 inherits from the topology that we have on the plane, and then there will be a point that will cause problem, which will make this not open, and that point is this point, this end point of this arc, which is present within this set. That other point is not present. This point will cause problem, because you won't be able to find any basis element containing this point and which will be entirely contained within this arc. You try to think of it, okay, we have already gone through this type of things many times before, so I am not going into an elaborate discussion on this. You see for yourself why this point causes a problem and prevents it from being open, and that is why f inverse is not continuous, in spite of f being continuous and also bijective, and that makes f not a homeomorphism. And finally, we have example 7, where we consider this function g from this interval, but this time onto R2, the entire plane, and that to obtain by expanding the range of that f from example 6. That means the rule for the function g is just this, and the domain is also this. The only thing is that we expanded the range from S1 onto the whole plane. Now this function g is injective and continuous, but not an embedding. Why is g injective? Well, what did we do to get g from f? We just changed the range, because our original f is bijective, and injectivity, so it's injective as well, and injectivity has nothing to do with the range. It's all about the function rule and the domain, so injectivity is retained. And at the same time, g is also continuous because f is continuous. You will see why these things are true more easily, than using calculus again to prove continuity. You will more easily see these things as consequences of general theorems on continuous functions that we will prove in the next topology video. For now, let's just accept that this g is also continuous. But in spite of having these two properties, g fails to be an embedding. Why? Recall what an embedding is. For an embedding, you have to have the function injective first of all. Okay, g is injective, but then what should you do? You have to replace the range by the image set of the function. Image set of the function means image set of the domain under the function. Because of the way we have obtained g from f, that image set is just this S1. And then we have to see whether that modified function is a homeomorphism or not. It's not a homeomorphism. From the previous example we get that, and that is why this g is not an embedding.